scholar at Duke University's Nicholas Institute for Environmental Policy Solutions. I'm an adjunct associate professor at Duke Marine Lab, and I'm the international chair at AMUR, which is the Institute for Marine Law and Economics, which is at the University of West Brittany, at the European University Institute of the Sea, part of the LabEx, the Lab of Excellence here in Plouzne, France. What I want to talk to you about today, some of the social science aspects, weighing the trade-offs and the use and value of living and non-living resources in the deep sea. There's a great deal of attention being paid right now to the extraction or the potential future extraction of minerals from the deep sea. You could see different kinds of minerals listed there on the left. There will be other video presentations in this series about what these minerals are, what kinds of metals can be extracted from them. I won't go into that now, but I do want to point out that deep sea industrialization and extraction is already underway for oil and gas in the Gulf of Mexico, in the North Sea, and there are plans for drilling off the coast of Brazil in the deep sea. In addition to that, methane hydrates have been discovered around the world in the deep sea, and there are countries like Japan who are quite interested in trying to figure out how methane hydrates can be extracted in a commercially feasible and profitable way. Of course, deep sea extraction goes back even before modern times. Now we have big factory trawlers that are able to trawl the deep sea while they're trawling for living resources, primarily fish. The extraction that occurs in this trawling is essentially very much like the kinds of extraction we'd expect from minerals. That is, the top of the seafloor is scoured and ecosystems are damaged in the process. This has happened for quite a long time, well before the advent of modern trawlers, and scars from deep sea trawling can be seen in a variety of places, including the deeper parts of the Mediterranean Sea. So the things I'm going to talk about, I may focus on minerals, but they really apply to all kinds of environmentally damaging extraction in the deep sea. From a social and an economic perspective, we have a series of questions that we have to ask when we think about whether we should extract in the deep sea. Of course, whether and where to allow extraction, how much to extract, how to extract, what limits should be placed on ecological impacts during the extraction, and how much damage in the end needs to be repaired. In the mining world, as well as in other types of industrial extraction, we often refer to these different steps as part of the mitigation hierarchy. That is, where and whether to allow extraction is part of avoid those areas where you shouldn't be extracting because the environmental costs are high. Reduce or mitigate impact, that's done by best management practices, activities that can be undertaken by the industry involved to limit the effects of environmental damage. Of course, there's always a cost to reducing environmental impacts, so we have to be aware of how much we're willing to allow in terms of environmental impacts and how much we expect industry to pay to reduce these impacts. And finally, how much damage needs to be repaired. This is what we talk about when we talk about restoration. Each of these different kinds of questions requires systematic analysis and thinking to understand whether it's worth extracting, whether it's worth taking the extra steps to reduce environmental impacts, whether it's worth restoring these areas, and how could we maybe better use those ecological and economic resources. I want to focus in today on this first question, whether and where to allow extraction, but I think you'll see that the basic concepts apply to each of these questions. When we think about whether to extract or not to extract, we can divide our thinking and our decision parameters into several groups. At a meeting of scientists, ecological restoration professionals, and economists in France, we decided on three different categories of decision parameters that we thought captured the social side of decision. Those were anthropocentric factors, what we would think of as economic decisions, societal decisions, and decisions based on governance and governance practices. We came up with another category of decision parameters that we thought more reflected ecological concerns. We call these ecocentric factors. These are the kinds of concerns that scientists have when you think about ecological function and rarity. And then finally, we have to recognize that all of our activities in the deep sea face a relatively high degree of technical difficulty, and there's uncertainty associated with the outcomes of the activities we undertake. These technical and uncertainty factors apply across the board to the decisions that we have to make in the deep sea. Among the economic factors that we have to consider is what's the value of the resources that are going to be extracted. Some of the resources in the deep sea, like gold and cadmium, the rare earths, have very high value, and the value on the market, the value for human uses, is considerably higher than the cost of extraction. The higher the value is, the more likely one would think society would be to be willing to allow extraction. On the other hand, we know that things like the abundance and supply of oil and gas keeps increasing, particularly because of new discoveries of gas. We also know that alternative energy sources put a limit on how high the price of deep sea energy can go. And so deep sea energy may have a lower net value in the long run compared to the cost of impacts on ecosystem services. And of course, we also have things like sand and gravel mining and phosphate mining. So we have to consider what's the value of extracting these resources to society compared to the costs. The value is high, then we're more likely to extract. The value tends to be higher when the things that we want to extract from the deep sea have few substitutes elsewhere. When there are many substitutes, that tends to push the price and value of these resources down. We can look elsewhere than the deep sea for these resources. So many substitutes leads us to not extract in a particular place. I talked about the price of metals. You can see that the price of copper, the price of nickel, and the price of aluminum have climbed steadily. Nickel and copper are two important elements that we find in these deep sea mineral resources. Oil prices remain high, stubbornly high, despite new discoveries that I mentioned about gas and despite increasing alternative energy sources. So that's what continues to put pressure on the deep sea from the international oil and gas industry. It's still profitable economically and financially to extract in the deep sea. And we have to recognize that there are real economic benefits to extracting resources from the deep sea. So of course, profits reflect the net value to the industry undertaking the activity. These profits can be captured locally through taxes and royalties. So if you are the Gulf Coast of the United States or Papua New Guinea, these energy resources and potentially mineral resources represent a larger amount of potential income for the country that can be used to boost foreign exchange. It can be used to support jobs, to build infrastructure, and to pay for government operations. So you can see why many developing countries are really trying to pursue these deep sea minerals. Many developed countries have been extracting oil and gas for their high value for quite a long time. In addition, the revenues brought in from extracting minerals and energy from the deep sea may have wider social and socioeconomic impact goals. Often these revenues are not just about increasing profits, but it's about trying to combat poverty, trying to achieve energy independence. This is, I think, particularly important for a country like Japan and its interest in methane hydrates. Mineral independence, particularly for rare earth metals. But we know that so much of the modern economy, from cell phones to television to information technology, requires minerals. The extraction of these minerals and energy resources often bring high-skilled labor to a country, and that has benefits as well. On the other hand, the discovery and extraction of resources, particularly in small countries, can lead to higher inflation, corruption. It can significantly change local cultures and affect local cohesion. So there really are positives and negatives from the social and cultural side of things that have to be weighed in thinking about what's the economic and social impact of the extraction of these resources, just from the point of view of the resource themselves. Now, one of the challenges of understanding whether we should allow extraction is understanding what are the economic costs and benefits. So we have a pretty good handle on the economic benefits of the resources extracted. Much more difficult to understand at this point is what will be the ecological and environmental costs of extraction. We don't yet know enough about how deep sea and high seas ecosystems work. We know that the high seas and deep seas are important to people. There are deep sea fisheries. There are pelagic species that live in deep sea areas that are caught as part of high seas fishing. But these species and organisms are also caught within EEZs and support local fisheries. The Global Ocean Commission has come out with a new report that details some of the key findings about high seas fisheries that applies to a lot of deep sea. We don't know how changes in the deep sea floor and the benthic ecosystem will affect these fisheries. We don't know how they'll affect other economically important species, particularly marine mammals. We don't know how they'll affect the ability of these areas to sequester carbon, which of course carbon kept in these ocean systems is carbon that doesn't get released into the atmosphere, and that has economic value. It's often difficult to understand the impact of a single deep sea extractive activity because we don't know what its relative size is to similar habitats in the global deep ocean. That's because we've only really mapped out biodiversity in about 5% of the entire seafloor. So much of the deep sea's ecosystem are unknown, so it's very difficult to know whether the destruction of benthic habitat is a relatively large or relatively small proportion of representative habitat, how big the scale of, say, the damages caused by a plume from deep sea mining might be compared to naturally occurring plumes, or what the area damaged is as a proportion of total similar ecosystem area. It's also true that the impacts of individual mining activities may not be easily added together. That is, we know that the ocean is a place where there are cumulative impacts from sound, from pollution, from sediments and plumes and loss of habitats, loss of forage. The benthos is part of the broader ocean ecosystem, as are the fish and the plankton and the crustaceans and all the invertebrates that live there. And we can talk about the ecological impacts of a single extraction event, but how do we put that in the context of many extraction events happening simultaneously or sequentially? And if we don't really understand what the cumulative impacts are from an ecological perspective, it obviously makes it very difficult to value the impacts of these effects in terms of ecosystems and the services they provide to people. Of course, governance and policy also affect our willingness to extract in the deep sea. There are international treaties and conventions that promote the use of deep sea resources for the benefit of all humankind. And so the International Seabed Authority has been set up in part to help humankind benefit from the mineral wealth of the deep sea floor. But there are also international treaties and conventions like the Convention on Biodiversity, the targets that were set out in Rio, Naichi, and other kinds of international agreements that require individual states and actors consider the impacts of their activities on biodiversity, ecosystem functions, and environmental quality. So you can see the tension here between the international bodies and treaties that promote extraction of the deep sea, international bodies and treaties that promote protection of these same areas. Within the United States and in other countries, there are also laws and resolutions and other types of governance that promote energy independence and mineral independence. I mentioned that before. Recently, Senator Blount in the U.S. has proposed a bill to promote the extraction of thorium from the deep sea, because thorium is an element that's important industrially in the United States. There are also environmental laws and regulations within EEZs and internationally that apply strict environmental regulations even to deep sea extraction. And the stricter are those regulations, the less likely it may be to extract in a particular place. Ecocentric factors include things like ecological vulnerability. That is, if an area is thought to be particularly rare, if its organisms are endangered, if it has unusual organisms, or there's some other ecological vulnerability associated with the site, all things being equal, that's the site you want to avoid. On the other hand, there are large parts of the deep sea that are already degraded, that may have low ecosystem services or low ecological function, low ecosystem value. Those are the areas where, all things being equal, one might be more likely to extract. I mentioned relative scale. It's hard to talk about deep sea extraction and industrial activity as if one size fits all. The footprint of deep sea extraction varies a lot. So you can have the very small footprint that's associated with mining near hydrothermal vents, like the proposed mining in Papua New Guinea near the Solwara 1 and 2 areas. That small footprint, it may be, I think at this time it's predicted to be 0.11 square kilometers. And that might be a relatively small proportion of ecosystem habitat area that's represented by these places near hydrothermal vents. On the other hand, the scale of manganese nodule extraction is thought to be very, very large, as is trawling. There are different estimates of the area that has been trawled in the high seas and the deep seas, and the amount of damage done to the seafloor. I believe Lisa Levin at AAAS mentioned that her calculation found that as an area as big as perhaps Canada and the U.S. has already been badly damaged by deep sea trawling. And then there are all of these other kinds of activities like phosphate mining and sand and gravel mining that also may have a very large footprint. Of course, the footprint of the ecological activity may be different than the overall expanse of environmental impact. So for instance, if you have a site that acts as a source for larvae or as a nursery area then loss of that site may affect a much larger ecosystem. Go back here for a second. You may also think about the ecological impact of unintended consequences like an oil spill. So, for instance, the ecological footprint of the Deepwater Horizon rig is relatively small. The ecological footprint of the oil spill that came from the accident at the Deepwater Horizon is quite large. The larger is the ecological impact, the less likely to extract. The smaller, the more likely to extract. But it's important to consider there's the planned physical footprint, and then there's the unplanned, unintended footprint of possible environmental damages that come from unforeseen events. Whether or not they're greener alternatives also makes a difference. So much has been made in the deep sea mining industry of the fact that the overburden, that is how much earth you have to remove to get to the mineral, is really small in the deep sea compared to terrestrial areas. The ecological damage in the deep sea will also be much smaller than much terrestrial mining. So if there are greener alternatives to deep sea mining, then you'd be less likely to do deep sea activity. If there are fewer green alternatives, then you're more likely to do the deep sea activity. So think, for instance, about there are fewer alternatives to mining that are potentially greener than what's happening in the deep sea. On the other hand, when we think about where we get our phosphates in our energy, there might be many more green alternatives outside of the deep sea. So in that case, we wouldn't want to extract oil and gas in the deep sea. We think we can get that same energy someplace else in a greener alternative. Pebble Mine here is one alternative for energy that's being considered as very, very high impacts. The rate of recovery and disturbance is important. When natural rates of recovery are high, you would be more likely to extract. So near hydrothermal vents, for instance, there's naturally high rates of recovery. Damage done there is likely to be repaired naturally much more quickly than, say, damage caused by mining in the abyssal plain, which may take millions and millions of years to recover naturally, if at all. So if natural recovery happens more quickly, you'd be more likely to extract, all things being equal. If recovery is slow, you don't extract. And of course, natural recovery is a function of both natural disturbance regimes and also the fragility and resilience of the deep sea ecosystem. So ecosystems that are fragile, have low resilience and slow recovery are places we want to avoid. High recovery, high natural disturbance may be places that are better targeted. Okay. And of course, related to this is the longevity of impact. Some of these impacts are relatively small, relatively short-term impacts. Some of them are very long-lasting. The precautionary approach would say avoid those long-lasting impacts until you really understand the damages. It's important to know whether we have the ability to protect important habitats that are like those that will inevitably be damaged by extraction in the deep sea. If we don't know that representative habitats exist, we don't have a way of providing protection to these habitats, then we should not extract in those kinds of ecosystems. If we do have good knowledge that there are other representative habitats that are known and protected, that is, they're likely to exist beyond the life of the mine, then all things being equal, we would be more likely to extract. Now, of course, we learn a lot when we do deep sea mining, and much of what we know about the deep sea has come from the collaboration of scientists with the deep sea industrial community. So when we think we can discover something new through the process of extraction, or certainly exploration, that pushes us towards extraction or exploration. On the other hand, there will certainly be times in the future where we won't be learning a lot through a future extraction activity, and in that case, the discovery of new science really doesn't play into our desire to extract in that area. So you're not going to learn anything, and science doesn't lead you to want to extract there. It's important to recognize that there's a lot of variation in the benefits and impacts of deep sea mining. This is a map produced by the Duke Marine Geospatial Ecology Lab. It shows what we know about biodiversity on the seafloor. You can see red is high biodiversity, blue is low biodiversity, and white is where we just don't know. So the first thing is we don't know a lot about biodiversity in the seafloor, particularly the deep and high seas. But what we do know shows that biodiversity tends to be highly concentrated. So it's not randomly distributed. We need to be careful to avoid these areas of high biodiversity. You can see the Gulf of Mexico is an area of high biodiversity. Parts of the North Sea are also areas of high biodiversity. This map here, created by David Moreno-Mateos of the CEF, part of the CNRS in Montpellier, shows different kinds of mineral and energy deposits that we know about in the deep seas and high seas, also coastal waters. The polygons represent areas where the International Seabed Authority has awarded exploration leases. So you can see that just as biodiversity was distributed heterogeneously, deep sea resources are also distributed heterogeneously. And the goal here now is that you can take this heterogeneity and try to avoid places where there are high environmental costs of deep sea industrialization, and instead try to identify those places where the benefits from minerals and potentially other kinds of resources are high and environmental impacts are low. What we've done here is we've just mapped out the different kinds of biodiversity impacts in International Seabed Authority areas. And what you can see is that some of these lease areas are thought to have much higher biodiversity than other lease areas. So the places that are red have high biodiversity, places that are blue have lower biodiversity. But even within the areas that the International Seabed is managing through its leases, there's a great deal of heterogeneity in the potential impacts of mining. So if you start to think about these different parameters that I've laid out, you can start making decisions about whether you should extract in the deep sea or not. So just as a thought experiment, I've laid out some of the yes or no's, extract or not extract, for different kinds of deep sea industrial activities. So for trawling, for instance, if you just do a thought experiment, what you find is that most of the factors for whether or not to trawl line up in the don't trawl category. The net value is not particularly high. There are lots of substitutes to seafood that's caught through deep sea trawling. The societal goals are relatively limited. This is mostly factory level trawling. These systems are ecologically vulnerable. There's a wide impact, and on and on. So you can see, just thinking this through, there are very few reasons a priori to think that deep sea trawling is a good idea. When it comes to oil and gas, it's sort of a mixed bag. The net value is potentially high in some places. In other places, it's less high. It depends on the quality of the resource. Yes, there are plenty of substitutes which would lead us not to extract in the deep sea. In some places, certain societal goals can be met where oil and gas contributes directly to economic development, but also don't forget that many places, many countries have signed climate change treaties, have emissions goals, and so extraction of oil and gas in the deep sea works counter to meeting those goals. Ecological vulnerability impact falls on both sides, but tends to be more in don't extract. New science, representative sites and longevity, you can do deep sea oil and gas so that it does create new science that we do place deep sea oil and gas away from critical areas and guarantee that representative sites are available. The longevity of impacts is still unknown. We're still unaware of how long-lasting the effects of, say, the oil spill associated with the Deepwater Horizon is going to be. Mining phosphate, something that they're considering off of the coast of Africa, and that tends to line up almost squarely in the don't mine area. All of the factors suggest that mining is not a good thing. There may be high net value, and you could argue that certain societal goals will be met by phosphate mining, particularly in places like Western Africa, if the ecological impacts are high, and there are plenty of alternatives to mining phosphates in the deep sea. Should we mine minerals in the deep sea? Well, it really depends on what we're mining and where we're mining. As I've mentioned, minerals can have very high net value depending on the mineral extracted. There are, in some cases, few alternatives, economic substitutes, which tends to push us towards mining. Certain societal goals, particularly for underdeveloped countries, are met, and this is one of the criteria that the ISA uses to give out leases. But it's not true that deep sea mining is important for societal reasons for all those who are going to be involved in deep sea mining. And clearly, many of the countries, if not most of the countries involved in potential deep sea mining, have to abide by other international treaties and conventions. Okay. Again, on the ecological side of things, mining can be preferred or not preferred, depending on where the mining takes place. So there are less ecosystem impacts potentially in dormant sites near dormant hydrothermal vents or in abyssal plains. Clearly, active vents have high ecological vulnerability as do the areas around them. Seamounts are often noted as places of high economic value. Similarly, the scale can be small for SMS extraction, but very large for phosphate and manganese nodule extraction. So the decision on an ecological basis of whether to mine or not to mine really depends on the mining activity being undertaken. And the same thing for green alternatives, new science, offsets, etc. So it isn't clear that there's one good answer about whether we should mine or not in the deep sea. It really depends on the minerals extracted, the value of those minerals, the ecological damage that's created, the availability of substitutes in other places. So to wrap up, if we are to take a prudent approach in the deep sea, there's certain activities that I feel clearly should be stopped. Deep sea trawling should be stopped because by all the criteria we've listed, it doesn't seem to make societal sense. Oil and gas is not a clear case for extraction, so we need to be very careful and prudent about how we move forward with oil and gas. We have to recognize that nearshore oil and gas extraction may have a bigger ecological impact on humans than in the deep sea, although on the other hand, the risks associated with extracting energy in the deep sea are much higher than in coastal areas. And finally, the real key here in doing oil and gas is to remove the subsidies that make oil and gas seem more beneficial to society than they really are. Try to better incorporate all of the environmental costs into the industrial and societal decisions about oil and gas. For deep sea areas, we should only move forward with deep sea extraction where we know the economic value of doing so is very, very high, much higher than the cost because the cost is still uncertain, particularly the cost to ecosystems and ecosystem services. I think we should start small so we can develop an understanding of the ecological impacts. We clearly need to avoid vulnerable and rare habitats. We need to favor areas that will recover naturally because this will reduce the ecological impacts over time and the economic impacts associated with them. We should make sure that we are certain that ecological damages could be offset elsewhere even if restoration on site doesn't make sense because it's too expensive. We need to have representative sites before we undertake deep sea mining. And we have to be quite honest about what's the real potential for restoration at a site. And finally, it's important to get the best science out of deep sea mining that we can as it happens. It's not just about moving industry and technology forward, but also moving our scientific understanding of the deep sea forward. Thank you very much.